Questions on any of the assignments so far? So, what we're looking at today is more roots, more dealing with these radicals and roots. And here, we're going to be dealing with some operations to start with, so addition, subtraction. Now, we are able to add and subtract like radicals if the index and what's inside are the same. So the first one here, both of these have the fourth root of 10. Now the fourth root of 10 is as simplified as it gets. 10's only products or factors are 2 and 5, so we can't simplify the fourth root of 10 because we need a number times itself 4 times to be able to simplify it as one of its factors. And it doesn't have that. But here we've got 1, and the other we have 7. So guys, so looking at this here, so we have the fourth root of 10 plus 7 times the fourth root of 10. So how many would we have?
7 fourth root of 10 squared.
So how many do we have here?
4.
Because how many fourth roots of 10s do we have?
2.
1. How many do we have here? 7. So we have a total of?
4.
So now another way we can look at this is they both have fourth roots of 10 in common, yes? So if I factored it out, if I factor 4 roots of 10 from 4 roots of 10, we have 1 plus, here we would have 7. So I have 1 from here, 7 from here. Well, 1 plus 7 is? Which would give us 8 times the fourth root of 10. Or I have 1 of them, and I add 7 of them to them, so we have a total of 8. Now, the same thing is true with fractional exponents. So 8 to the 1/5, we can't reduce, because 8, if we took the cubed root of 8, it would be 2, but we can't take the 5th root, because there's only 3 2's in 8. But 8 to the 1/5 is the same in both of them, yes? So here we have 2, here we have 10, so we have a total of
12.
times 8 to the 1/5. So any questions, guys? Any questions on A and B? So let's look at C. Now again, for us to add or subtract, the radicals have to have the same root and the same number inside. Now, one of them is 2 and the other is
4.
So for us to be able to subtract these, I need to have both terms to have the cubed root of 2. Now the reason I picked the cubed root of 2 is, well, one of them has the cubed root of 2, yes? Can we reduce the cubed root of 2 any further than what it is? But the cubed root of 54, there's a good chance we can reduce it. We can simplify it. Now there's 2 ways we can go about that. One is looking at the factor tree. So looking at 54. Well, 2 is a factor of 54. It'd be 2 times 27. 27 is 39, and 9 is. So 54 is the same as 3 to the 3rd times 2. Which means the cubed root of 54, if we wrote this in, is the same as what? The cubed root of 3rd times. Well, what is the cubed root of 3 to the 3rd? So we have cubed root of 3 to the 3rd times the cubed root of 2 Cube root of 3 to the third is 3, but we still have the cube root of. So the cubed root of 54 is the same as 3 times the cubed root of 2. And we could have put that underneath it, or we can set it up as this here. Now can we subtract these two? Yes, because they both have cube roots of 2. 3 cube roots of 2 minus 1 cube root of 2 is? Cube roots of 2. So with some of these here with the addition subtraction, if the roots or the numbers aren't already the same, we need to make them be the same. Questions on this so far? We ready for the next one? All right, guys. So let's look at number 10. 7 fifth roots of 12 minus the fifth root of 12. It's going to be what?
7. Oh wait, minus. Yeah.
Minus 1. 6 fifth roots of 12. Because fifth root of 12 is as simplified as it gets. Because there's not going to be a factor of 12. That would be a number to the fifth power. And we can just subtract because we do have those both the same. Here we have 7, here we have 1. 7 minus 1 is 6 times fifth root of 12. The next one we have 4 times 9 to the 2/3 plus 8 times 9 to the 2/3 would be times 9 to the 2/3. Now the last one, we have the cubed root of 5 plus the cubed root of 40. For us to be able to add or subtract, we need the radicals to have the same number inside. So we know the cubed root of 5 is fine. But we need to simplify the cubed root of 40. And we can do this off to the side, because 40's factor tree would be what? 5 and 8. So that would be 2 cubed times 5. Now we could write it in here and say the cubed root of 2 to the third times 5. Cubed root of 5. Now the cubed root of 2 to the third is 2, yes? Because when the exponent and the number in the index are the same, they simplify out. But this is still being multiplied by the cubed root of 5. So what is the cubed root of 5 plus 2 times the cubed root of 5? And that's it. Questions on any of this here? We ready for the next one? Properties of rational exponents and radicals can also be applied to expressions involving variables. Because a variable can be positive, negative, or 0, sometimes absolute values are needed. Because what we're talking about here is in a more general sense. We know, I'm just adding this in, the square root of x squared is going to be what? X. It's just going to be an x value, yes? But do we know in this case what the value of x is?
Oh no.
Because we could say x is negative 2, yes? Now if we work this out, negative 2 squared, take the square root of it. Well, the negative 2 squared is 4, and the square root of 4 is 2. So is the x that we started with the same as the x that we ended with? No. And if we look at this here, when x is even, we take the even root of an even power. What we get is the absolute value of x. And if we look back at what we had, so the x that we started with is negative 2. If I take the absolute value of negative 2, we get, and it will match with what we have. And that's what they're really talking about with this here, is in the general sense, when we talk about a variable where we don't know if the number we're starting with is odd, even, sorry, not odd, even, positive value, negative value, or 0, we add the absolute values when we're taking the even root of an even power. Because here, the fourth root of 3 to the fourth is 3. The fourth root of negative 3 to the fourth is still 3. So if we take the even root of an even power, we have to add the absolute values to those variables to offset that sign change. Odd roots, it doesn't matter, because the seventh root of 5 to the 7 is 5. The seventh root of negative 5 to the 7th is negative 5. So we don't need it. It's just for if the root and the power are even. So we want to simplify each one of these expressions. Now the first one we have is the cubed root of 64y to the 6th. Now, we can look at this in two parts. We can look at the cubed root of 64 is being multiplied by the cubed root of y to the 6th. Now the cubed root of 64, we can try plugging it into the calculator. Because if we plug it into the calculator and get a decimal answer, then we can use the factor tree to work it down from there. However, the cubed root of 64 is 4. We don't have to do that. We can just say that this is 4. Now, what would the cubed root of y to the 6th be? So, let's look back at this here. Nth root of a to the x is equal to a to the x over n. Now, we didn't apply this with the 64, because 64 cubed root of 64 in the calculator works out nicely. But also, 64 to the 1/3 doesn't mean any more to us than the cubed root of 64. However, with this variable, the x in our case would be what? 6. The n in our case is 3. Now we can reduce 6/3. How would we reduce 6/3? Or what would it be? 2 over 1, which is just 2. If there's still a fraction, we simplify the fractions to whole in our parts. The whole numbers come out of the radical, the parts stay in. But here, we get this here. We get 4y squared. Now we don't need the absolute values for this here because y squared will take care of any negatives. But we can leave it here. Now, for the most part, we're not going to focus too much on powers or the absolute values, applying those, but I will mention them here. I won't take off points in the homework, but I will point them out in the note sheets. Any questions on A? Any questions on the first one here before we look at the next one? The next one that we have is the fourth root of x to the 4th over y to the 8th. Now we'll do the same thing here that we did with the fractional exponents. But the first thing I would do is split it up into our 2 here. Y to the 4th over x to the 4th on top, y to the 8th on bottom. Now at this point here, we can rewrite the numerator and denominator as fractional exponents, because the numerator is going to be x to the power inside is 4. Our root is 4. Or as we can see here, the 4th root of x to the 4th is just going to end up being x. Now the denominator y, our fractional exponent, the number on top is the exponent with y, which would be 8. The denominator is the root, which is 4. Now 8 over 4 is 2. So the 4th root of x to the 4th divided by y to the 8th simplifies to x over y squared. Now this here is technically where we need the absolute values with x. We don't need it with the y squared because a number times itself is going to be positive. So we don't have to put absolute values with the y squared, because if the value of y was negative to start with, the y squared would make it positive. If it was positive, it's going to stay positive. However, since x is now to the 1st power, we need the absolute values to adjust for that sign change. I'm not going to count off if you don't put it in the homework, but again, I'm just pointing it out here so that we can see it. Any questions on any of this here?
Nope.
Let's look at the next one. The 3rd root of 27 times d to the 12th. And we look at these here, especially with numbers. We can break it into the multiple parts. So we can say the cubed root of 27 times the cubed root of d to the 12th. And the first thing I would do is, in the calculator, look and see what the cubed root of 27 is. And if it is a nice number, like it is here, 3, we can simplify it to 3. The cubed root of d to the 12th. What we can do is rewrite this as a fractional exponent to see how this simplifies. Now for the fractional exponent, the numerator is going to be the exponent attached to our variable, which is 12, and the root is 3. Now 12 divided by 3 will simplify to 'Now we don't need the absolute values around our variable d because we have the 4th power. 4th power, if it was negative, the 4th power will make it positive. If it was positive, it'll stay positive. Questions on any of this here? We good with this one here?
Yep.
Let's look at the next one. So we're going back to division. And with the division, let's split it up into the numerator and denominator. So the numerator would be the 4th root of x to the 4th. The denominator is going to be the 4th root of y to the 16th. Now looking at this here, I think we can say what the numerator is. The 4th root of x to the 4th is going to be what? Yeah, it would just be x. And the reason for that is because of our rational exponent. The number on top would be 4, our exponent. And the number on bottom would be the index of our radical, the number inside the little v. And well, 4 divided by 4 is 1, so we just get x. Now the denominator, we'd have y to the 16 over 4. And 16 divided by 4 is going to be 4. Yeah, we would put the absolute values around the x because it's an even root and an even power. So we would need that there. Whenever we have an even root and even power, and it simplifies to an odd root, odd power, we need the absolute values. Questions on any of this here? Rewrite each expression in simplest form. Assume all variables are positive. Since we're assuming all variables are positive, we don't need absolute values for any of this here, because we only needed the absolute values just in case we took an even root of an even power and got it to simplify. Here, we're just assuming positive. That way, if a variable does come out, we're not having to put absolute values around each one or having to add additional notation. To where when the variables come out here, if we did have one that come out and we need the absolute values, we don't have to write it in because we're assuming that they're just going to be positive anyways. So we're going to take the fifth root of each one of these here. So we'd have the fifth root of 4, fifth root, 8, times the fifth root of, times the fifth root of c to the fifth. Now the first one we're looking at is the fifth root of 4. Can we take the fifth root of 4? No. Because with 4, the most we can say is it's 2 squared. That's not going to simplify. Now let's rewrite the rest of these as fractional exponents. A would be to the 8 by B to the fifths, and C would be to the 5/5. 5/5 And again, we want to simplify this. Now, on all the previous ones that we've done today, the fractional exponents reduced. Kind of like here, c to the 5/5. The 5 over 5 reduces to, does 8/5 reduce to a nice number? No. Because if we look at this here, fifth root of 4, I'm going to write this in as a mixed number, because 8/5 as a mixed number would be what? 1 and? Because we have the whole number and then the parts that are left over. So if we look at 14/5, because we'll still have fifths. 2 and 4/5. Now we could do this in a calculator. 14/5, 2.8, 14/5. So second here. So we're seeing how many times can we take 5 out of 14. So we can take it twice. 5 and 5 is 10. So we take 10 away and have 4/5. C to the first, yes? Yep. Now, in simplest form, we're still going to have the fifth root. Because as we see with A and B, and our 4, we do have the fractional exponent, yes? Because these still have a part left in the radical. Because the 1 and the 2 are the numbers, they're variables that come out of the radical, and the fraction is what is left inside. Now we still have what? The 4, because we said we could not take the fifth root of 4. The 4 has to stay inside the radical. Now let's look at A. A's was 1 3/5, yes? So how many A's come out? 1. How many stay inside the radical? So 3/5. The fifth is part of what? The fifth is the index, and the exponent is the 3, because we're going back to our nth root of a to the x is equal to a to the x over n. As the x is attached to the variable, the n is the root. Any questions on what we've done so far with these first two? Let's look at B. How many come out of the radical? 2, because we got 2 whole parts out of the fifths. And how many are left inside? 4. And C, how many come out? How many stay inside? 0, because 5 over 5 reduced to 1. And that's it. So really with the variables for here, since we're taking the fifth root, each group of 5 of those variables that we can simplify out come outside. So with 8, we can take 5 away from it once. So one of them comes out. 8 minus 5 is 3. We have a to the third left inside. B to the 14th, we can take 5 away from it twice. And if we take 5 away from it twice, we're left with 4. C, we can take it once. Questions on this here? Okay. Yep. And we'll come back to that in a minute. Actually, let's look at another one of those, because I think looking at one more of those will be helpful before we move on to the next type. I do need to rearrange these notes. So the first thing we'll need to do with this here is to break it up into our parts. Can we take the cubed root of 2? Can we rewrite 2 as a number to a power? No, 2 is prime. So we can't take the cubed root of 2. So in our final answer, we will have the 2 still left inside the cubed root. If it had been 8 instead of 2, we can take the cubed root of 8. Cubed root of 8 is 2, so we could simplify it. Now, looking at the rest of them, a to the 13, it might be easier to see this as a fractional exponent. Same with b. Since the exponent is 3, 3 is on top, and our root of 3 is on bottom. And lastly with c, the number on top of the fractional exponent would be 8. The number on bottom would be 3. Thirteen thirds would be what as a mixed number? Because we can take 3 away from 13 4 times. I mean, we could write that out over here. So 13 minus 3 is 10. 10 minus 3 is 7. 7 minus 3 is 4. 4 minus 3 is 1. We can't do it again. So we did it 4 times. There's our whole part. And then we put the remainder over 3. So 4 1/3. B. Can we, well, 3 over 3 reduces to B. or b to the first. C, 2 and 2/3. We can do the same thing. 8 minus 3 is 5. 5 minus 3 is 2. We can't take 3 away from it again. We did it twice, so 2 is our whole. And the fractional is 2/3. So let's rewrite it back. Well, our 2 didn't simplify at all, so we leave the 2 inside the radical. A, how many come out of the radical? How many A's come out? How many A's stay? 1, because we had 1/3. The 1 is the exponent, the 3 is the root. B, 1b comes out. Since it was a whole number, none of them stay inside the radical. And lastly, C, how many come out? How many stay in? And that's it there. Any questions on any of this here? All right, let's look back at this one here. Yep. Looking at this here, x, the numerator is fine because we've talked about these before. The numerator having a radical is fine. Here it doesn't. But we cannot have a radical in the bottom of a fraction, yes? Now there's different ways to look at this. But again, if I'm taking the cubed root of y to the 8th, I need that fraction to simplify. I need that radical to simplify, yes? Now, let's go on and rewrite this denominator as a fractional exponent. So the number on top would be 8, and the number on the bottom would be 3. Now, if the numerator had a radical, we can leave it alone because that really doesn't make a big difference as long as it doesn't simplify. But we need this to simplify. We need the radical in the bottom of the fraction to simplify. We need that fractional exponent to not be fractional anymore. We need the fraction to reduce. Does 8 divide by 3 evenly? What is the next number after 8 that would divide by 3? 9. How many are we missing? So what we can do is multiply the top and bottom of this by y to what fractional exponent? Over? Because we have the 3 on bottom to match up with our root, match up with what we already have, the 8/3. We need them to both be thirds. And in the denominator, when we multiply like bases, we add the exponents. So 8/3 plus 1/3 is? Now, since the numerator, x and y, are not like bases, we just multiply them together. In the denominator, 9/3 is the same as 3. 9 divided by 3 is 3. Do we have any more fractional exponents in the denominator? No, which means we don't have any more radicals in the denominator. Now, the numerator, we can rewrite y to the 1/3 back in radical form. The index, the number in the little v, is going to be what? 3. And the power with y is 1, but we don't have to write it in. So x over the cubed root of y to the 8th in simplest form, or in simplified form, is x times the cubed root of y over y cubed. Questions on this here? we're going to look at one more of these here. Actually, we will pick this up tomorrow. We will finish this tomorrow.